All right, so welcome everybody here and online to our, to our final CESO seminar of the year. For today's speakers, we're very excited to have Frank Cascarano here in person and David Marasco over Zoom. These are two instructors in our very own physics department here at Foothill, so we're very excited to kind of hear a little bit about their stories, and they're going to talk about a recent trip that they made. I guess it's on the title slide here is the NASA's Airborne Astronomy Ambassador Program, where they visited an aircraft that has, effectively from what I understand, a very large telescope on it. We're going to hear a little bit more about that, but yeah, we're really excited to, we've had some outside speakers, but it feels very special to have some of our own members of our own Foothill community spending time with us today. So thank you to you both for participating, and I will give it off to you.
Thank you. We're ready.
Does it show up?
We're good. Okay.
I can see it on Zoom.
All right. So NASA has a program, their Astronomy Ambassadors Program, and David and I were selected this year. Actually, David has done it in the past also, but the program had changed enough since they started it that they wanted him to participate again. And the idea is there's a few objectives, but one is NASA wants to get information out to the public about all the great things they're doing with your tax dollars. And one of the best ways to do that is to hit teachers, because if you hit up a teacher and then they can tell all their students, then you can get that information out to a lot of people. And so they involve teachers in these programs. This was the 9th cycle of teachers that went through that we were involved with this past year. And they bring in about 30 teachers a year from all over the country. In our group there, the picture you see there, one person, those are 2 middle school teachers. One was from Reno, Nevada. One was from Anchorage, Alaska. And David and I, of course, here from Foothill. And so they had teachers from all over the country involved, those 30 teachers from all over, middle school, high school, community college. And in addition to this, one of the things that they provide the instructors with are really well thought out hands-on experiments that are relevant to the type of science that NASA is doing today. It's not, you're not repeating some experiment that was done 250 years ago. You're doing a hands-on lab work, really well thought out experiments that they've put together for us that's relevant to work being done today. Anything you want to add to that, David?
Oh, there's lots of stuff I can add. First of all, it was great that you and I flew together, but Jeff Matthews is going to be flying in a few weeks. So Foothill is actually sending 3 people this year. For a long time, it had been restricted only to high school teachers. This year, they opened it up a little bit and went for middle school teachers and 2-year college teachers. This program actually predates SOFIA. I have met people who were part of a similar program who flew on the Kuiper Airborne Observatory when Kuiper ran before SOFIA. And that's about it. That's the additional information I'd have.
Thank you.
Not to be confused with Sophia Kim.
So this is an infrared telescope. So let me just give you a quick background as to what infrared means. The electromagnetic spectrum, everything that's above absolute zero radiates energy in the form of electromagnetic waves. So if something is really, really cold, it's going to radiate at very low energy. That would be in the radio wave spectrum. As you warm it up, it starts to radiate energy at higher and higher energy levels. So as you warm something up, it would start to radiate in the microwave portion of the spectrum. And then eventually in the infrared, you and I radiate in the infrared part of the spectrum. And then as you heat something up a little bit more, it starts to give off a little bit of visible light. And the lowest energy visible light is red, so it starts to glow red hot. And as you heat something up more, it gives off all the colors of visible light. That makes white, so something glows white hot. And if you heated it up more, it would look mostly blue. And then as you heat it up more, it would give off mostly ultraviolet and then X-rays and then gamma rays if you could heat something up hot enough. Now, our eyes are only tuned to a very small section in the middle there. And so we call that visible light because our eyes are tuned, the antenna in our eyes are tuned to that part of the spectrum. But all this stuff is really the same. There's no difference really as far as the physics is concerned between a radio wave and an X-ray and visible light. So IR, infrared, is just below slightly lower energy than visible light. And so if you can look at things in the infrared, you can see things that aren't hot enough to give off visible light.
So one thing that I was reminded was once, and I love to point out, is our eyes are very good at seeing the visible spectrum. But if you walk outside and feel that warm sunlight on your body, your skin is actually a good detector of infrared light. So you can think about it and you say, we sense light in two different ways.
David, you want to talk to this slide?
Sure. So this is this is a nice picture of the constellation Orion. And the left-hand side, we see it in visible light. And we have this big orange star in one corner, that's Betelgeuse. If you think back what Frank was saying a little bit before, the colder you are, the more red you're going to glow. Betelgeuse, if we could see into the infrared, is actually one of the brightest stars in the sky. So what we're seeing is a small portion of the light that Betelgeuse is actually putting out. Most of its light is going to be infrared. And diagonal, there's this bluish star on the other corner, that's Rigel. And it's kind of doing the exact opposite. Rigel is this super star, and it's putting out most of its energy in ultraviolet light. But of course, this is all light that we see with our eyeballs. And the nice thing is that it will show you things that you can't see otherwise. So here, what we're seeing are kind of warm clouds in this constellation, and this is where new stars are forming. So you kind of get this idea of places where there is interesting things going on with physics, but it hasn't reached the point yet from a astrophysics point of view where it can pump out visible light. So we can't see it with our eyeballs or our normal telescopes. Does that mean it's not interesting? No, it's tremendously interesting. We just need different tools to view it.
Yeah, I forgot to mention when I was talking about the spectrum, this is something that you can see. You can go outside at night and look at the stars. Some of them appear white. They would be the same temperature as our star, the sun. They would look the same color. And some appear red. They are cooler than the sun, cooler than our star. They give off more light in the red. And David pointed out that there's one in this constellation. And then some look blue. They're hotter. They're giving off more blue light. And you can see that at night when you look at the stars. And then one of the things that was described to me on the trip was that, of course, to look at something in the visible part of the spectrum, it's got to be hot. It's got to be giving off visible light. But if you're interested in how stars form, well, it's not hot enough to give off visible light yet. The stars haven't formed yet. So you have to look in a different part of the spectrum. And IR is looking at that lower energy light. So you can see things that are cooler temperatures. And so a lot of the studies that we were looking at, they're looking at chemistries that are taking place in star forming regions. And astronomers are learning a lot about how stars form. David, you mentioned the Kuiper Observatory earlier. You want to talk a little bit about the transition and why an airborne telescope?
Sure. So I actually believe that there was an airplane prior to Kuiper where somebody probably just got like a much smaller airplane and stuck a telescope out the window. But prior to SOFIA, we did a lot of work with the Kuiper Observatory. I think the rings around certain planets in the outer solar system were actually discovered with the Kuiper Observatory. And it's the exact same deal. We take an airplane, we put a telescope on it, and we use it as a platform to view stuff in outer space. Now, one of the things that we haven't talked about infrared light is that it's very hard to do infrared astronomy from the surface of the Earth. And you say, why is that? And the reason is water vapor in our atmosphere. So water vapor in our atmosphere does a very good job of blocking infrared light from getting to the surface of the Earth. So if you just had a telescope down in San Jose and you said, let's look at something interesting in the infrared, you point your telescope up and there'd be all kinds of problems. The infrared light has difficulty penetrating through the atmosphere. So there are a number of different ways of handling this. One is to just try and get rid of as much water as possible. So you'll have people down at the South Pole in Antarctica. And that works because Antarctica, the South Pole, is so cold that all of the water is frozen out. So when I was in graduate school, a big set of my friends would go off to Antarctica every winter. And you say, why the winter? Well, because it's summer in Antarctica. And they would go off and they would do infrared observations at the South Pole. Okay. The other thing you can do is you can try and get above as much of the water as possible. So there are attractive volcanoes out in Hawaii that are very tall, and you build your telescopes out there. So all of my friends in graduate school were doing things like going to Hawaii and the South Pole. And I said, I guess I should have been an infrared astronomer. Once you get past sort of the South Pole and the top of the mountain solutions, then there are solutions like the one we have here, put it on an airplane, get above as much of the atmospheric water as possible. And then of course, the ultimate solution is, hey, let's get above all of the atmosphere. Let's just get an infrared satellite and put it in outer space. So then you turn around and say, well, what's the trade-offs between an airplane and outer space? Okay. Outer space will get you above all of the water. Outer space will allow you to take observations 24 hours a day. On the other hand, with outer space, once you have your telescope in outer space, you're done. You can't fix it. You can't repair it. A lot of telescopes need to be kept cold and have limited supplies of cryogens, which keep them cold. So there are a lot of telescopes that were sent to outer space that had a set lifetime. When they ran out of their coolant, they were done with that phase of their mission. Okay. With an airplane, you can shed some of those restrictions. So when you have an instrument on your telescope in outer space, that's it, you're done in outer space. With SOFIA, every 4 to 6 weeks, they take the instrument which is mounted to the telescope and they replace it with another one so you can do different science. So same telescope, different detector means a whole other branch of science that is now open to you. The detectors on SOFIA, a lot of them need coolants. But of course, you just walk over to the telescope and you say, well, I'm going to fill this up with more coolant for 24 hours, and then you're good to go. So you sidestep the entire coolant issue. Because you can replace and service your instruments, if something goes wrong, you literally fix it. So when Frank and I were in Southern California in February, one of SOFIA's main instruments was literally on a lab table all opened up because something had gone wrong. They took it down to the lab and they were fixing it. Okay, that's impossible if you're in orbit. When you're in orbit, if something breaks like that, you're done. And of course, the last thing is, it takes a long time to plan a space telescope. By the time it's launched, a lot of the technology is a little bit obsolete. With an airplane, you can always go in and do upgrades and introduce newer and more modern instruments. So it's a way of hedging against obsolescence. So that's a lot of reasons why a plane is attractive versus a satellite. Of course, with an airplane, you would have issues like you could only fly it a certain number of hours a year versus 24/7 in outer space. And sometimes mission planning for airplanes gets more complicated, and we'll talk about that a little bit later.
And there's the initial cost. I mean, running an airplane is expensive. Let's not kid ourselves. But if you want to make it look cheap, think about the cost of putting a satellite into orbit, and it makes it look very reasonable all of a sudden. And then just to reiterate on what David said here, these are, I know these numbers don't mean a lot to you, but the fact is that even though all 5 or 6 of these instruments are operating in the infrared part of the spectrum, they're all specifically designed to look at different areas and be able to observe different phenomena. So we wanted to touch on a couple of highlights from SOFIA's mission. And one was the confirmation of water on the sunlit surface of the moon. So they were able to confirm that. They knew that there was hydrogen in the soil on the moon, but they didn't know what form it was in, if it was in the form of water or not. And SOFIA had a mission that confirmed that. There's not a lot of water in the soil in the moon. It's less than in the soil in the Sahara Desert, but they were able to detect that with their telescope. And then another highlight is the Pluto occultation. So an occultation occurs when an object passes in front of a distant star and it blocks its light. And from when that happens, you can get a lot of information about the object. Did you want to talk about this a little bit more, David?
Oh, sure. What's important about this is 2 things. So first, SOFIA or another airplane is the only way you're ever going to be able to take this measurement. So you talked about an occultation is some object goes in front of a star. In this case, it's Pluto. Pluto goes in front of a star. So of course, we're going to be in the shadow of Pluto. But that shadow of Pluto isn't going to be over the entire Earth. It's going to be in a very specific part of the planet. And it's actually going to just sort of sweep across the planet very quickly. So unless you have already built an observatory in the exact right position where the shadow of Pluto is going to sweep across the face of the Earth, you're never going to be able to take this measurement. The strength of SOFIA is we can literally put it just about anywhere on the planet if we have enough planning time. So people knew this occultation was coming. They knew that we were going to get great science out of this. So they flew SOFIA to exactly where it needed to be. Got SOFIA in the air, and as the shadow of Pluto is going across the face of the planet Earth, they flew SOFIA in that shadow so they could take data. And my recollection was they were literally getting sort of updates of exactly where the shadow was so they could aim the airplane that much better. So this is unique. Only one telescope on the entire planet could have taken this measurement, okay? And then you say, well, what did it tell us? Well, we look and we've got this graph in here, and the big thing that we got out of here was basically details about the atmosphere of Pluto. And when we later went and had the New Horizons telescope fly by Pluto and observe that system, it was important that we had as much information as we could about Pluto going in so we could do flight planning for the New Horizons mission. And this gave good information just in terms of A, basic science, and B, more information so that you could fine tune a later, more important science mission.
Yeah, you would expect, just to tell you a little bit about this graph, if Pluto had no atmosphere, as it passed in front of the star, it would cut the light off, And so you'd expect this shape not to look like a W. You'd expect it just to look like a straight line down, flat on the bottom, and then a straight line up the other side. But because there's an atmosphere there, as Pluto moves in front of the star, first the atmosphere filters out some of the light, and so you get a slope. You get that W shape, you get the slope coming in. It's not a steep line, it's sloped. And then when Pluto completely blocks the star, the atmosphere, which we're familiar with because just this week we had a lunar eclipse, right, where the moon looked red because the atmosphere of the Earth was bending the light. It was refracting around the Earth, scattering, and the red light could light up the moon. Well, the same thing happens here, and you get that central peak in forming that W. And so a lot of information about the atmosphere in this graph. And here's just some details about the trip. It's they bring us down to Southern California. The SOFIA is out of Palmdale, which is Armstrong Flight Center, which is very close to Edwards Air Force Base. You take off at night. It is a telescope. It's infrared, but still, if you're out during the day, the detectors are just flooded with sunlight and you can't see anything. So you have to fly at night. Takes off roughly 8 p.m., lands about 6 a.m. So a good 10 hours every night that it flies. And it flies at very high altitude because you want to get up above as much of the atmosphere as you can. Most commercial flights are sort of in the 36, 38,000 foot range. And we were flying in the 43 to 45,000 foot range. So pretty high up in the atmosphere. We talked a little bit about costs earlier. Each flight consumes 220,000 pounds of jet fuel. Yeah, the 747s, old 747s are not very fuel efficient. 3 pilots, 2 telescope operators, 3 scientists, 1 or 2 mission directors, and a safety officer, in addition to visitors and ambassadors like us.
The only couple things I'd add here are that there are some very strict rules around when they can land. So what they worry about is there's this big door in the side of the airplane that they open up, and then the telescope is exposed to the heavens. If they can't close that door and protect the telescope from sunlight, basically the sun will hit the telescope and fry a lot of the stuff downstream in terms of the detectors and everything else. So their concern is the telescope door close, and my understanding is that it always has, but if the telescope door doesn't close, they have to land the plane and either get it into a hangar or get it in such a way so that the shadows involved would protect the telescope from being struck by direct sunlight. So that's a big restriction around their landing times. They're always trying to get in early enough so that that's not going to be an issue. Frank talked a little bit about fuel being consumed. At cruising altitude, they are burning a gallon of gas every second. And granted that the engines are designed to do flying rather than driving, I watched the fuel gauges as we left the hangar to get to the runway before we even accelerated down the runway, just to go from the runway, we need 1 ton of fuel. So yeah, like Frank said, these are not efficient airplanes just in terms of burning jet fuel.
So we get a map like this, and it's a little bit of magic, and I think they're getting a little bit better. David said he got a map like this for his first flight that looked like a rat's nest of lines, back and forth, crisscrossing the sky. And now ours all looked pretty normal, like a loop that the plane was flying. But you can see we're taking off from Southern. These are 2 different flight paths that we were on. We take off from Southern California. I've sort of penciled in California and the Canadian border, and fly out over the Pacific Ocean, up over Canadian airspace, and then back down to Southern California, completing a big loop. And the telescope, it has, you know, a lot of motion up and down, but it really doesn't turn left or right. The plane has to be oriented properly for it to aim it left and right. So that's why you see these lines where the plane is flying in a certain path for a certain amount of time. That's one experiment. Each one of these legs is one experiment. The telescope is aimed at a certain point, and it has to be, the plane has to maintain that direction to keep the telescope aimed where it is. So they were telling us that if they encounter some turbulence up ahead, they want to take a different path, the plane can shift over and then take a parallel line that follows one of these lines on our curve. So they can go parallel to it and keep collecting data, but then they might hit the next line, the next leg of their journey at the wrong time. And sometimes if they get there too early, they'll have to do a little loop, kill a little bit of time, and then they join back up with their flight path. So they're constantly checking that. That's what the flight director, one of the big jobs the flight director does, is monitors things like that and has to make adjustments if there's bad weather or something that they have to divert around.
So I actually had the opportunity to talk to the person who makes these maps, and I believe it might be their full-time job. There's an amazing amount of complexity that goes into these maps. So first of all, each one of these maps is a scientific target. So people went out and said, well, I want the telescope aimed at that star or that cloud or whatever for these scientific reasons. And if you saw a couple of slides ago, SOFIA's got like 7 or 8 instruments that get used. So each one of those scientific proposals will say, well, I want to do this using instrument 1 or instrument 5 or instrument whatever. So first of all, this is a set of targets that all decided that they wanted to use the same instrument because they don't change the instrument except once every 4 to 6 weeks. So first they have to go through all of their scientific proposals and say, these are all the ones that are using this rather than that. As Frank said, you steer the telescope by steering the plane. So you have to have this thing where you fly for a certain number of minutes pointed in a certain direction. And of course, at different months of the year or different times of the day, that object might be in a different place in the sky. So you have to have that planned in. What I didn't know, but I was told later, was some of these are, in essence, fainter objects. So you want to have this, you want to see them in the best possible conditions. So that means you want to be even higher in the atmosphere. So some of these things only get looked at later in the night when SOFIA has burnt enough fuel so it can actually go all the way up to 45,000 feet rather than 42 or 43,000. So there's even thinking about, do we do this early in the flight at a lower atmosphere, or do we do this later in the flight at a higher altitude? Of course, you take off in the morning or take off at night. You have to build yourself a plan so you actually get back to where you started at the end. And you see all of like these little red splotches on this map. That's restricted airspace. So you have to go and either avoid the restricted airspace or negotiate with whoever's in charge of the restricted airspace. So there are all kinds of these things that really make planning these little loops very difficult. But it is somebody who's got a lot of experience and probably a very good set of software helping them out.
About the only negative I can think of from our trip is that we were kind of hoping, we had our fingers crossed, we knew we were going to be flying up over Canadian airspace. We were kind of hoping we'd see the northern lights, the aurora borealis. We did not see any. But that didn't stop everyone from telling us how great they were the day before that we got there.
So we did not get to see the Aurora Borealis, but I was in the cockpit. And when we were coming down and landing on the Friday flight, I got to see St. Elmo's fire, which is electrical discharge from the airplane. And that was super amazing. It's like, oh, it kind of looks like we're being struck by lightning, but no, that's just us shooting off electrons because we're coming down and we're rubbing through some stuff.
And one of the things, the highlights is just meeting all the people involved and talking to them and finding out about their journeys. There are pilots, there are telescope operators, the scientists, and we got to interface with them quite a bit. The telescope operators, all women with bachelor's degrees in astronomy or physics, and they got their job at NASA pretty soon after graduating. I wanted to capture the pictures of these two because they both went through the community college system prior to transferring. And then this pilot we met, she had a very interesting story going through and she got trained, her pilot training through the military. And at the time, the military didn't train women to be pilots. So she found out that the Navy was finally, they were the first branch to accept women into their pilot training program. But she decided for some reason to sign up for the Air Force. She got there, she told them she wanted to be a pilot, and they said, we're not training women to be pilots. So she stuck it out. And then a couple of years later, the Air Force opened up their program to women. And she just had this attitude like she wouldn't take no, just the door closed and she kind of ignored it and kept plowing forward. And eventually the door opened. And she really had a great attitude. And she was in the military for, 10 or 12 years, and then a civilian pilot. And now she flies for NASA. And then the scientists were telling us that one of the things they like about working for NASA is, and I didn't realize this at the time, but I guess it makes sense. Most scientists that are having their data collected don't go up on the airplane and don't go to telescopes. The data gets sent to them electronically. And so the scientists that run the instrument, they're the ones that are there. So a lot of times people will, other scientists will include them on the paper so that they have sort of a representative there on the instrument. And part of their job is they get sort of relief time to publish papers. So part of their job is to publish findings. And so, and one of the things that was interesting for us, one of these scientists, I forgot which one now, but one of them, their experiment was running on the night that we were flying. And so that's kind of unusual too, that they're there taking their own data. David, you want to add anything about?
Yeah, these people were amazingly friendly and satisfied in their jobs. And some of that is it might be lonely to be on an airplane for 10 hours a night and just see the same few people. And it might also be that due to COVID restrictions, I think we were the first group of educators they had seen quite in a while. I'm sitting in my bedroom right now with COVID, so I can understand, hey, I'm kind of lonely. I want to see more people. But these people were just great. And literally just going out to dinner with us. Okay. It's not, hey, I'll see you on the airplane. But it's, hey, it's some burgers. And the group that we're looking at right here, they're based out of Davis. So, I mean, this is literally people where you could be working with them next year if you transfer to Davis.
The good and the bad here. It was announced earlier this year that SOFIA's mission ends this year, September 30th. They're cited the high operational costs, and so SOFIA will be no more. But we didn't want to end on that note. So let's reflect on the positives here. It had a very successful mission with scientific discoveries, and this program that we were involved with, the Astronomy Ambassador Program, will continue on. They've already taken applications for next year, and they're going to be using a land-based telescope, I think, in Hawaii. So the teachers will go there and get to see how the data is collected on a land-based telescope and how the science is playing out in that setting.
Yeah, so I talked to people at NASA, and what they would tell me is that SOFIA is the second most expensive telescope that they operate. And that includes the telescopes that are in orbit. So the writing has been on the wall for SOFIA for a while. In fact, one of the things that I think kept it going for longer than you would expect is that it's kind of an interesting structural program. NASA only pays 80% of SOFIA's bills. The other 20% come from the German Space Agency. So 20% of the flights are, in essence, flown with German personnel. One of the other things about that is anytime SOFIA needed a major maintenance service, it was done by I believe a Lufthansa crew out in Germany. So you'd fly SOFIA to Germany, and part of the financial arrangements where it would be that the German company would do the overhaul for SOFIA. And this international agreement, I think, made it a little bit harder for NASA to just sort of say, we're pulling the plug. But that situation could only save them for so long. Frank says successful 8-year mission. I think it was longer than that. They're trying to do cycle 10 experiments. And I know that there was a cycle 0, so certainly they were flying before they were claiming to be year 1. I think that there were some really great scientific discoveries that came out of this program. And I can tell you that it kind of feels like when I move in sort of these scientific circles, especially the high school science circles, somebody will see me wearing my SOFIA jacket and they'll say, oh yeah, I've got another friend who did that. So it's not that every high school teacher in America got to do that. That was never the goal, but it's one of these, Kevin Bacon type games. It's like, somebody who knew somebody who did it. And, that's really what it boils down to, is that there was a decent amount of penetration into sort of the high school teaching community.
So that concludes our talk on our experience with SOFIA. Were there questions, or how do you want to?
No, I can
handle it?
unshare the slides. They don't see it.
Yeah, now it's just the speakers, yep. Any questions, Bud?
You didn't talk very much about the detectors. Is it possible to create an infrared science project here in one of the clubs to build a detector and demonstrate a little bit of infrared spectroscopy that mirrors, if you will, something you do here?
We, so we've done sort of taken some baby steps in that direction. So what they provided us for a lab activity, which David and I have both run, is a little solar cell that will also respond to infrared light. And then the students made a circuit that would so they could basically modulate a light source, an LED infrared light source. And so we played music through it and shined it at the solar detector and then played that back through a speaker. So they got to see that they could get infrared light to carry information, and we could transmit that information over the light and get it back and play music through a speaker. That's so we didn't make the detector, we just used a solar cell. You were thinking more advanced than that?
A step beyond that.
Yeah.
Then you could play the music of the spheres.
Yeah, that's something to think about.
I have a question. So you talked about one of the experiments that was conducted, and it was confirmation of water on the moon, right? And then you said that they knew there were sources of hydrogen, but not exactly what type. So I'm just curious, what were some of the other contenders? Like, was it hydrogen sulfide, or like how, because you can distinguish those by IR pretty readily, I would think. So I'm just curious if you know anything more about that.
I don't.
Yeah.
David, do you have anything?
I'll give a more general comment.
Maybe Jeff.
Okay, I'm going to give. Go ahead, Jeff.
I was just going to say, off the top of my head, I don't know what other molecules were being considered. I mean, other than, sort of the classic thing to look for is OH, the OH ion. Is that somehow getting trapped? But other possibilities, I should go read the paper.
I wasn't sure if it's that or like maybe some simple organics or something like that. Yeah.
So my more general comment was that if you look at some of the capabilities that we are losing now that SOFIA is being sunsetted, SOFIA, one of the instruments, was very good at being able to take very fine resolution spectra in the infrared. And that let us, in essence, to be able to do all kinds of astrochemistry that we might not be able to do anymore. So these flights that Frank and I were on, there was a lot of, okay, we're going to look at some very specific chemical bonds. And then these would come out in spectra and be like, oh yeah, the shoulder of that spectra is a slightly different than what you would see normally. And here's the chemistry behind that. I don't know that the instruments that we have on our other infrared telescopes have that finer resolution that could do that science. So we're losing a little bit of astrochemistry, I believe.
Cool. All right, so are there any other questions, either in person? I asked the people at home, seems a little bit quiet.
Oh, that's a question.
Or Raymond first, maybe, and then.
So you said you were on the flight for 10 hours. Did you conduct any like experience, like your own experiments up there, or did you just like view other scientists conducting experiments?
So the process for getting your experiment on, you have to apply. There's an application period, it closes, then they're peer reviewed. They said that about, what was it, 1/3? Does that sound right? Get accepted.
Mm-hmm.
So a lot get rejected. Some of those people then apply the next year. So this is a long process to get some of them are applying the second or third time, they finally get accepted. And then that's for the year. Then it might be 8-9 months or so before your experiment actually flies. So that's the process for getting your research accepted and getting data from the set. So we, operating those instruments, you have to be, you have to know what you're doing. You have to be pretty highly trained. It's very specific stuff. So we didn't operate any instruments, but we were there. We were watching them doing it, taking the data, talking to them, and the person that facilitates the whole thing is really good at, because you go up there and you're like, oh, I don't want to bother this guy. He looks like he's busy, or I don't want to interfere there. But the person that facilitates is really good at, is it okay if the ambassadors come up here and talk to you now? Yeah, go talk to them, and he keeps you moving. And so we get to talk to everybody. We get time to sit in up in the cockpit, talk to the pilots. We get time to talk to the operators, the scientists. And so you're really moving around and getting a feel for what they're doing and asking them questions as they're doing it. Did I answer your question?
Yeah.
Jeff, you want to add something or comment?
I might have a little bit of interest in the answer to this question of, the aircraft is flying at higher altitudes than typical commercial aircraft. And so are they still maintaining the same pressurization, the same temperatures? Or is it, is there a little bit of physical discomfort going along with this?
Bring a sweatshirt, Jeff.
That actually depends upon two variables. Variable number one is the instrument. Some of these instruments just like to run a little chilly. The 2 times I flew, the instruments were not these chilly instruments, and I was fine just wearing my jacket. The other thing I think it depends upon is the mission director. So some mission directors are a little bit more sensitive to the comfort of the crew and the passengers, and will tell the pilots, okay, this is what the environmental controls are going to look like tonight. And then others are just kind of more utilitarian. That has been my experience.
Yeah, both of our flights were fairly comfortable, but we heard horror stories that they keep it, it's really cold. And at first it doesn't sound so bad, but think about being in that temperature for 10 hours. I mean, that it creeps up on you, and that would chill you to the bone. So I'm very happy that ours were fairly comfortable.
Can I ask a question? This is just because I'm a layperson, but I'm curious to hear from each of you. What was like the most exciting thing in the experience, whether it's something you saw or something you got to talk about, or yeah. I know that's very general, but
I think the whole, just sort of seeing the whole operation and what's involved, and the crew, how many people it takes to run the plane, and what's involved behind the scenes, and it's really a fairly big operation, keeping the instruments tuned up, and when they're not on the plane, when they're not installed on the telescope, there's a lot going on. And then just, the people involved, meeting all of them, like David said, really nice folks, finding out about some of their paths to that position. Those are kind of the things that stick out in my mind.
So sorry, go ahead.
For me, it was kind of more a philosophical realization. So when I was a graduate student and I was still sort of doing science, I would use X-rays to look at surfaces that would grow on top of silicon crystals. And these are very intense X-rays, so you literally could not be in the same room as the as your experiment. So you'd sit there and you control your experiment by a computer. You'd have a script that would move mirrors and send light into different places, and the light would hit your sample, and then you'd have a detector that would say light from this sample is coming in and being detected. And then you'd go and you take that data and you'd have to do all kinds of data massaging to it to turn it into something sensible. And then you'd sit down and you write a paper. And it felt really kind of narrow and unique. And there are like, 12 people on the planet doing the sort of similar enough stuff to you. And then I'm on this airplane, okay? And what's going on? Well, there's somebody sitting at a telescope and they type some stuff into the computer, and the computer runs a script. And what does the script do? Well, the script moves mirrors to send light to different places, okay? Well, then there's a detector. What's that detector doing? Well, it's collecting information from light, and that light is going to tell you about whatever the heck you're observing. Oh, well, can you do that from the data that comes right out of the telescope, the detector? Oh, heck no, you have to sit down and you have to do all kinds of complicated adjustments to take care of this and take care of that and take care of the, the fact that the atmosphere is 1% argon and nobody else on the planet cares about that, but it will affect your data. So it's kind of this universality of science. It's like, okay, I think I'm trapped in this very narrow field, but literally here's somebody who's doing something that would get published in a completely different journal that I would never read, and they're literally doing the same thing as I am. We're just looking at different objects, and we might have different theoretical frameworks, but I'm at a computer moving a mirror to do light. The data is being collected. I have to spend a lot of time distilling these data. And it felt like that with 6 months of training, I could teach that person to do my old job and they could teach me to do their job. And that felt very exciting and unifying. And we're all scientists and we're doing this together. So that was very sort of neat and special to me.
Cool.
Question?
Yeah, I was just curious, like, you saw the shot of the plane and then the bay open or something, I think, but wasn't much detail of like what that equipment looks like. Is it basically one big optical column and then it's split off to the different sensors? Or are there multiple instruments, looking into space? What is exactly is the equipment side is in there?
They will bolt one detector onto the telescope at a time. So light comes down from the telescope, it hits the detector, and I believe that most detectors that light goes to a very specific place and then is diffracted or whatever happens next. So it's not you can split this light off into 3 different beams and do 3 different observations.
So it isn't just one main telescope or.
So, yeah, remember the picture where the door opened in the plane? So that's where the main light collector is. And that never changes. That's always there. And the light then gets funneled through the bulkhead there that seals the cabin for pressure and everything. And that's where the detectors, the instruments get bolted on. So so there was a particular one on there that looks mostly at the chemistry that's taking place in these regions. They can remove that and put another one on that looks at slightly different regions. But that's on the interior part of the bulkhead. It straps on the door that opens. That detector always stays the same.
So basically, when you design an instrument that you want to be part of this mission, you have to have an adapter of some sort that's going to be ready for it and to fit right on, or
right. So yeah, so there's the instruments. Every once in a while, they'll take. It sounded like they would take in proposals for a new instrument. That did not happen very often. And in fact, there were 5 or 6 instruments, 6 instruments, I think, total on this on the tool. And so that part didn't happen very often, but yes, there are these specs for how much it can weigh, the maximum size, how it would mount, those types of things for sure. So most of the proposals for experiments all fit into one of these 6 instrument categories, and then they group them and give them out.
One of the stories we were told is that there was a instrument that was being developed, and at one point they realized they couldn't get the instrument through the door on the plane. And the person designing the instrument said, well, why don't you just cut a bigger hole in the plane? And they're just like, well, that's not going to happen. I think we need to end this conversation right now. And I don't think that instrument was ever completed.
All right, so we have one question in the chat from Brian at home, and I think we'll make this our last question of the afternoon. So the question is, how much of a difference is there in the infrared imagery from SOFIA versus IRFT/Spitzer? Is it obvious to the human eye? I don't know what he's referring.
I'm going to defer to Jeff.
Yeah.
Okay.
Yeah, so chiming in here real quick. So the IRTF in Hawaii, so the infrared telescope facility in Hawaii, it has a set of instruments that are sensitive only out to maybe 10 microns, just because atmosphere, right? Even being at the highest point, basically the highest accessible point for telescopes on Earth, being above, as much of the atmosphere as you can be, but still be on the ground. One of the driest places on Earth, you still have so much water vapor that the sky is opaque at longer wavelengths. And so there is some wavelength overlap. IRTF, primary mirror, is similar in size, maybe a little bit bigger. So maybe its images can get slightly higher resolution. Then when you go to Spitzer, Spitzer's detectors go a little bit further out in wavelengths, out to, I don't remember what its limits were, 24, maybe something like that. But SOFIA's wavelength range goes even beyond what Spitzer was able to see, even though Spitzer was off in space. And so this goes back to what David was saying earlier about we're going blind to a portion of the spectrum, right? We don't have, Spitzer stopped operating years ago. Herschel was operating in these same wavelengths, but it stopped operating years ago. And so there's this big gap between about 10 microns and about 800 microns that SOFIA has been in for the past, roughly decade. So I hope you don't have any questions that require observing molecules in that wavelength range, because if you do, and there's nothing on the horizon either for development in this range.
On that sad note.
Very awesome. I guess we can stand up here, but yeah, we just wanted to thank you both once again for speaking to us today. It was really interesting. It was cool to see, and for me personally, it's good for me to hear things outside of my comfort zone. So definitely got that out of it. So yeah, and then for those of you at home, thank you for attending. For those of you in person, and I hope everybody has a lovely afternoon and weekend. All right, everybody.
Thank you. Bye-bye.
Feel better, David.
Yeah, that was really